Hi, in this video, we're going to take a look at ordinal logistic regression. All right, so ordinal logistic regression, I'm in a situation where my target variable, the variable that I'm trying to predict, my dependent variable, it has an order to it, but it's not numeric. Okay, so I'm in a situation where maybe I have high, medium, low, 1 star, 2 star, 3 star, 4 star, 5 star, but I don't have like 5.6, 7.9, 8.2. I don't have numbers. All right, so in this situation, when we say high, medium, and low, if you're the judge, you may have seen that, you know, that's a low, but it's a high low. And, you know, this is a medium, but it's a low medium. While I, on the other hand, as judge, I would have looked at the same thing. And well, you know what? That's a very low low, and this is a very high medium. Maybe you're really close to high, but not close enough. And when we do ordinal target variable, like there's fundamentally like a gap that each judge has that's there, but we don't have it in the data. And so it doesn't make sense to treat like, you know, this as like 1, 2, 3 for high, medium, low. The same is true when we talk about stars or in ratings, that, you know, when we have discrete values for, you know, for evaluating what's going on, it doesn't, you know, if I want to make a prediction, it really isn't a good idea to try and do like regular old regression on this. We want to do something that, you know, actually picks up you know, these features of the data better than what like a numeric model would be able to do. All right. So normally in logistic regression, we only have 2 levels. Now we're going to be looking at modeling more than 2 levels, and they're ordered: high, medium, low, very low, low, moderate, high, very high. So where there's an order to it. Now for us, for the purpose of modeling, you could say, you know, high, medium, low, or low, medium, high. And the modeling mathematically would work out either way. It's okay. It doesn't really matter that much. But you know, we need to be consistent. Just be consistent through your data project, and you'll be golden. All right. Now, in general, the more levels that we have, the less accurate our model is going to be. Okay, so just across the board, this is from my experience. This isn't from me, you know, reading this anywhere. This isn't from a textbook. This isn't from a professor of mine. This isn't from an academic journal that I've read. This is from me modeling over and over and over. And I've seen that, well, you know, if I have more levels to be modeling to try and predict, the more opportunities for a mistake there are. And the more opportunities for a mistake, the more likely I am to make a mistake, roughly speaking. So in general, if we can, we want to bend our levels if we can. So let's say I have very low, low, moderate, high, very high. If it's okay with my stakeholders, I would like to, you know, start merging, you know, some of those together. So maybe you know, very low and low for this problem is the same thing, and very high and high is the same thing, practically speaking, from an operations point of view. Then I want to just put those, I want to say low or very low, high or very high. And then I've got, you know, instead of having 5 levels, I've got it down to 3. And so, you know, there's less ways to make a mistake. In that situation, you know, calling it low when it really would have been very low, or calling it very low when it would have been low, it isn't a penalty, isn't a mistake. And now I have to be in a situation that, you know, for my stakeholders, it's okay to not worry about this. So if you can, try to bend your categorical and ordinal levels as much as you can, if your stakeholders and your, you know, your business problem allow it. So, you know, we want to bend adjacent levels, you know, that are hard to distinguish between, you know, so, you know, like if I have like a very narrow range of like, one time I was modeling where I had 8 levels, and it ended up that levels 1, 2, and 3, this was, you know, test results. You know, it was like low 1, medium 1, high 1 in state of Florida testing data. And it was the criteria to land in each of those bins for a student was very, very narrow. So it was hard for me to get the right prediction. And so I went to my stakeholders and went, hey, I'm having trouble getting sufficient accuracy. No model is better than a bad model. I would rather not launch this model as is. It's okay if I, modify the data and, we make it into an easier problem for me to model. And they were good with that. They were okay. They were disappointed, but it's better to disappoint them with no information than to disappoint them with bad information. All right, so let's prepare the workspace. Going to suppress digits, avoid scientific notation, suppress warnings, clear my workspace of any gunk that's floating around, and I like piping. All right, so I'm going to use the BFI data set that's in the psych package. And I'm just going to go through and modify some things, just do a little bit of data prep, and just clear through some stuff. So just making this so that it's usable. And so now let's go ahead and visualize the target distribution. So here we have A5 is my target variable that I'm interested in. And I'm just going to do a bar plot by counts. And you can see, what we've got going on. Now, so we can see that 5 and 6 are the most common, then followed by 4, 3, 2, and 1 is the least. Now, I use the Veridis color palette. This is a good color palette for the colorblind, but you'll notice that labeling becomes a problem with this dark purple. It's possible to reverse the color, but that takes additional load, additional work. I didn't do it. It's a 59. It's visible, but it's hard to see. If this was for a full formal project with my stakeholders, my big boss, I definitely would have put some work into it. Now, a mistake would have been to just use the reverse colors of the Veridis color palette. That won't work out because the ones in the middle will get washed out. In that situation, I would have yellow for 59. I would have this green for 186. I would have this teal for this blue, and then this blue for this teal bar for the numbers. And that it wouldn't look very distinct on the middle too. And so you need to do like a reverse color situation. Okay, so first thing I'm going to do for modeling, I'm going to show you the dumb way. I'm going to show you the way that like a professor asked me, all right, how would you model this? Well, all right, well, I gave my answer. This is what I'm going to show. And this is not the best way. This is the dumb way. Has additional work. It's not parsimonious, but it's a tool in our tool belt. This is a useful way when I need to have more nuance in my models, when I have a large amount of data and the other techniques I'm going to show are not sufficiently accurate. This is absolutely like my last ditch choice if I'm having trouble modeling, but this is a tool in my tool belt. So what we're going to do in this approach is that if let's say that I have 3 levels, what I'm going to do, I'm going to make a model say, hey, it's 2 or 3. So I'm going to model the probability of getting level 2 or level 3, and then I'm going to make a model for is it going to be level 3? And so then I'm going to have for K levels, I'm going to have K minus 1 models. And so then you'll notice that for the lowest level, I don't actually have a model. I found this is pretty easy to understand. This has a lot of nice flexibility if I wanted different model structures for different levels. But in a moment, I'm going to show that there can be some major problems, especially if we have light data. All right, so what I'm doing here is I'm going to model, is my target variable greater than or equal to level 2? So it's level 2 or level 3, level 4, level 5, and so on. Here I'm going to say, hey, is my target variable greater than or equal to level 3? Then target variable greater than or equal to level 4, and so on. And so I'm going to have K minus 1 models going on. Now, if I go through and create like a binary matrix to represent my target variable in this format, each row is a non-increasing row vector. the column means decrease from left to right, and the reverse cumulative proportions of the target match the column means. All right, so this is saying that basically by coding it this way, I haven't lost any information. Same information, different presentation. All right, so here, this is my matrix of target variables. So this is level 2 or greater, level 3 or greater, level 4 or greater, level 5 or greater, level 6 or greater. In this presentation, a 1 means that it was 2 or greater, 3 or greater, 4 or greater. So now I know that it was less than 5. All right, so here row 1 was level 4. Now 2 or greater, 3 or greater, 4 or greater, 5 or greater, less than 6. All right, so I know it was level 5, level 4, level 5, level 5, level 5, and just to get some variety, level 3, then level 3, level 5, level 5, level 4, level 2. If it was level 1, it would have been all zeros. All right. Okay, so now if I go through and I just take the column means of this presentation of my target variable, and I go through, I take my target variable, create a table, switch that to proportions, take the cumulative sum and rearrange things in the right manner, you'll notice I get exactly the same proportions here as here. All right, and so this is, I just did this just to show you that by doing this presentation, I took a column vector of ordinal data and I recoded it in this binary matrix format. I have lost no information, and if I had to, I could recover it. All right, so now the approach of individual models is not a good idea in general. First and foremost, it's not parsimonious. In this situation, I would have 5 models to maintain. That's 5 opportunities for things to go wrong. So I don't like that. Also, we can have a situation where the probabilities don't make sense. Typically, this is going to be a problem when I have light data. But if I had big data, I would honestly consider like maybe random forest or stochastic gradient boosting that can handle multinomial anyway. So if I'm using the logistic regression approach, I'm probably in light data, or I'm in a situation where I'm like scientific research and I need the inference aspect. And so let's go ahead and show like this actually happening of the probabilities getting screwed up. The probabilities getting screwed up arises because these individual models, if I did 5 different models, we're going to have different slopes on the same predictor variables. And because of that, we can get intersections when I plot the probability curves. And where I have intersections is where we're going to have the things like not make sense. So let's go ahead and draw a picture to kind of show this to you. All right, so here, these are 2 curves that are not parallel with each other. All right, so let's say that red is the probability of 2 or 3, and the black is probability of level 3. So you notice that the probability of 2 or 3 has to be greater than the probability of 3, right? That's the only way it would make sense. Now, if I fit my model, if I fit these 2 models completely separate from each other, then it's not like the computer goes, well, let's make sure they match up. No, I haven't taken the time to do that. And what can happen because of the different slopes, you'll notice that over here, we're saying that the probability of having level 3 is greater than the probability of having level 2 or level 3. That doesn't make sense. That would mean that the probability of level 2 has to be negative. And so we want to avoid the approach of individual models for each level. All right, so now let's take a look at when is it parallel. So when it's parallel, you'll notice that these have exactly the same slopes. So these are parallel curves, and visually, if I just shift them left and right, they'll overlap with each other perfectly. I made sure of that when I built this. And so you'll notice that every time I look at an X value, going straight up, it hits black, then it hits red. It hits black, it hits red. It hits black, it hits red. And these are the parallel curves. The intercept will determine the horizontal distance between them. All right, so most of the time we want parallel slopes. The intercepts for each level will vary, but all levels have the same slopes for all predictors. So if I had 5 predictor variables when I'm doing ordinal logistic regression, every single predictor variable will have exactly the same slope, for all 5 models. And it'll be the intercept that varies to get things a little bit more tuned to the individual level. All right, so here is an example of me building a model, individual models. And what I did, I used very light data. I only used 10 observations. I fit, 5 models on this. And you can see that it doesn't make sense what I have here. This is saying that the probability of level 5 or 6 is greater than the level of, or the probability of having levels 4, 5, or 6. Doesn't make sense. All right, so let's go through and let's actually use parallel slopes. All right, for my exposure to R, the POLR function within the mass package is the most common one. I personally don't use it very often. I don't think I've ever used that at all. I use other ones. I use the VGAMs. That's usually the one I lean on because it just has a lot of tools to it. But this is a good approach. It's very popular in the R community. The the default case is for proportional odds logistic regression. The proportional odds is similar to multinomial regression, except instead of using a baseline level for all k-1 models, the baseline level is the level 1 less than the one being modeled. So when we do proportional odds, we're saying that the level 1 less is the baseline level. All right, and so here everything is pretty simple. At this point, we really just follow what we do in GLM pretty closely and run with it. We have our formula, we have our data, and do I want a Hessian? I usually produce it just to check it, produce a model. And here I want it to be a logistic method. And so we can see that we're going to get 1, 2, 3, 4, 5 different models, or different intercepts, and we're going to have the same slope every single time for all 5 of the submodels. And so here, remember, it's proportional odds. 1 is the baseline for 2, 2 is the baseline for 3, 3 is the baseline for 4, 4 is the baseline for 5, 5 is the baseline for 6. And we can get our results. If I want to predict the class, then when I do the predict function, I put type equals class. Now you'll notice this particular model definitely overshot it on the 5s. Now, if you were going to over predict on something on this particular one, over predicting 5 would be the one to do, but you can see that it completely missed every case of 1, 2, 3, 4. And this is, I didn't do a train test split on this. So this model is really just not favorable. Now here I can get the individual probabilities and run through it, and you'll notice that here there isn't as much of a difference as so here you would expect 5 to be more dominant in the probabilities of looking at it, but we'll notice that it's not that big of a difference here, which is also a sign. So the probabilities are looking pretty consistent to that original bar plot, which means that really I'm not picking up a whole lot of predictor variable quality on this one. And there's plenty of things to print out and analyze and get into. I don't want to spend a lot of time on this. Basically we get the same tools we have through the rest of statistics. Next one I want to talk about is the cumulative link model with the CLM function in the ordinal package. This package I don't believe is being maintained anymore, but through the archive you can download it. The reason why I like this is that we have control over more features with this. And so we can set it up so that I'm going to equal distance. We will restrict the distance between consecutive thresholds to be the same size. So the horizontal space between the slopes is constant. Symmetric restricts the distance between thresholds to be symmetric, a bound line around the center of our center level. Symmetric 2 restricts the latent mean in the reference group to 0. This means that the central threshold is 0, or that the two central thresholds are equal apart from their sign. And then flexible is what we saw before, where we allow it to just, anything is allowed, but we still have parallel slopes. All right, so I'm just going to go through and just run, just so you can see in the code how to do it. And you'll notice that I've got a different threshold every single time for this. And so we have our flexible model, we have our symmetric 2, our equal distance. And you can go through and just pick through all the things. And the reason why we would like equal distance and we would like the symmetry is that reduces the number of parameters I have. So if I'm in a hypothesis testing point of view, or I'm in light data, it's nice to have fewer parameters to have to test, to evaluate, to have to fit. And so it's advantageous to have fewer parameters. If I say equal distance, then what I have to do, I have to know the intercept for one, and then if I know the distance between, I know the intercept for all the others, just off of 2 values, instead of having to set up 5. And so we can set up spacing, and here central spacing. You can see that as I'm scrolling up, I have more parameters to work with. So here I have 5 parameters. Here I have 3. Here I have 2, and here I have 2. And so, the fewer parameters I have, the more parsimonious the model is, just, the better it will be if it predicts equally accurately as the other ones. And, we can get our coefficients and get our confidence intervals, just like in the rest of statistics. Get our summary, just like in everything else in R. Wait, I skipped some. Oh, we can run ANOVA. Now, the ANOVA test will use chi-squared instead of the F distribution. We can check. So here's something that's very nice, is that we can check the convergence. This is a very, very nice function to be able to execute this with, be able to dig in and make sure that things have gone the right way with my model before I start actually running it. And of course, we can make our predicted values off of it. And, just plenty of things. I'm surprised that this package isn't more popular now that I'm looking at it. I've never used it professionally, but it is on my list now. All right, next one is a proportional odds ordinal logistic regression using the LRM model. And so things are pretty much the same thing as what we did before. I grab the function, I put in the formula, I tell the data, and it works it out. And frequency of the responses, it does some nice hypothesis testing for me right out the gate, so I don't have to do it, I don't have to call it, I don't have to use summary or ANOVA. And I've got my coefficients, and you can see now the intercepts are presented very nicely here. That I think this is easier to interpret, easier to work with. Here's our ANOVA table, using the chi-squared distribution. And plenty of things to work with. Now, here's the one that I use most of the time professionally, and the VGLM in the VGAM package. This is a big package. This package is huge. This has a lot of tools, a lot of power to it, and this is the one that I professionally lean on. So here, when I'm doing ordinal logistic regression, I've got 3 approaches I can handle. So I can use ACAT. This fits adjacent categories for my ordinal regression model. Here, C ratio fits continuation ratio for my linkage function. And then I have cumulative, where I have a cumulative link ordinal regression model. And how do I choose which one? Honestly, what I've done is I do a train test split. I see which one gives me the best predictions, and that's the one I've used every time. Every time I've used this professionally, I've needed to be able to have inference and prediction simultaneously. And so they're like, I want good solid predictions. I have always taken the route of train test split on selecting which of the three to use. There are other tools in there. There are tons and tons of tools to use, but train test split is always a good approach. And so we can see our intercepts. And here we have our intercepts again. And so there's a good amount of flexibility. So basically, this is just modifying how the linkage function is built up in relation to each other, how it's fit. And we get plenty of things that we can pull out, plenty of things that we can analyze. This package has been good to me. I like it. It's a good one to use. I can get my AIC if I want to compare. Lots of stuff to dig into with this. All right, so if I'm doing ordinal logistic regression, most of the time we want parallel slopes. So most of the time I'm going to pick a function that does that. Now, if I'm in a situation where I'm having trouble getting sufficient accuracy, I could consider doing individual models for different levels of my ordinal target variable. Typically a bad idea. It's not parsimonious. We can get mathematical results that don't make sense. Typically, that last one is not an issue if I have a large amount of data. But if I have a large amount of data, I would also be considering other model structures. So, where's the advantage in it? Like random forest will just spit it out and handle ordinal for me, no problems. We also talked about the different ways to apply, to extend logistic regression to our ordinal target variable. And so lots of tools. Which one's best depends on your project. If you don't know, go through and do train validation test split. Go through that, follow those principles, check to see which model is performing the best. That's a good way to go. Different packages will have different ways to evaluate AIC, BIC, and so on. So it's, if I want to compare different models from different packages, don't trust the AIC from different packages, because this may be corrected, this may be uncorrected, this may be corrected with a different correction formula. I find that if I do training validation tests, it's consistent across the board, and use the same partition across all your models. All right, well, that's all I've got for you. Life is short. Do math.